Rebecca Hooper from the BLA is now going to talk about. We've talked about carbon reduction. Now we're beginning to examine net negative, and that opens up a very exciting opportunity for us.
So like everybody else, I'm going to start by thanking for the invitation. It's an absolute delight to get out of the house, and it's a delight to see some old and friendly faces. I know most of you don't know who I am and have absolutely no idea about Lyme probably, but I am very, very pleased to be here, and I hope that shows. As David said, I am going to talk about the potential to become net negative. This is about where are we going to be in 2050, essentially. So it's the big green button that says next. Yay. Okay, so I'm going to cover 3 items. It's going to be a bit of an introduction to the BLA. That's my job, so that's what you're going to hear about. I would be shot if I didn't tell you about those sorts of things. I'm then going to do a bit of egg sucking because obviously still hungry after lunch, and talk to you about Lyme in stabilisation. I'm sorry, but it's kind of what I have to do. And then the really interesting bit, which is about how we go to net negative. When I get to the bit on Lyme and stabilisation, it may not be perfect. There may be mistakes in there. Please forgive me. I hadn't realised that I was going to have quite such a technical audience. And I'm really frightened because I can see Nick, Tom and Paul in the corner. And I'm just thinking, oh, God. So if it's wrong, I'm really sorry. So introduction to the BLA, the British Lyme Association. We are members of the Mineral Products Association, which you may be more familiar with. We're like a department within that. There are 3 major producers in the UK. There's Lhoist, so that's LHOIST, that's Lhoist. There's Singleton Birch, which is much easier to say, and Tarmac, which everybody's heard of. We're all members of the MPA, so all members have to comply with the MPA Charter. We also have associate members, so again, a couple of slides down the road, I'm going to tell you why Lyme is important to everybody. It's everywhere. It's used in everything, not just construction. So that's why we have associate members, which are British Sugar, Speciality Minerals, who make precipitated calcium carbonates that go in your toothpastes and other cosmetic products, and Tata Steel. With associates, we collaborate on health and safety and environmental matters, and just so that it's a note to you guys, we've just published our annual SD report, which has just gone up on our website. So UK lime plants, so we all know that Buxton, clearly big centre for lime production. That's because that's where the really good calcium carbonate is. But we also have Singleton Birch based over in the Humber area. And then there's also, Lhoist have a dolomitic lime production plant at Whitwell in Nottinghamshire. So dolomitic lime is produced in a slightly different way, you may not be familiar with. It's produced in a very similar way to cement. It goes through a rotary kiln at a higher temperature. And then Tata Steel have their own production facility at Shapfell. So anybody who goes up and down the M6 regularly will have seen it. As you come over the top of the hill, it's on your, well, if you're coming down, if you're going up, it's on your left. If you're coming down, it's on your right. Load of kilns on the side, you'll know it. If you've seen it, you'll know it at Shapfell. And then Speciality Minerals are at Birmingham. And British Sugar are obviously producing where all the sugar cane comes from, the sugar beet, sorry. So that's manufacturing. Lime is really, really, really important. All the UK lime producers continued producing lime throughout the COVID pandemic because we have to have lime for societal purposes. It's important because it purifies drinking water, it treats your wastewater, it cleans up your sewage sludge. It's used to treating that. It does emission. It cleans out emissions from combustion plants, energy from waste, and other incineration processes, which clearly there was a lot more of that, importantly, going on during the pandemic. And it's also used, as I've noted, in primary materials, foods, chemicals, plastics. So maintaining a continuous supply is really, really important for the UK. Now, you guys are obviously interested in it from a construction point of view. Construction is not the major use of lime. This shows the various different breakdowns. In 2020, we produced about 1.1 million tonnes, which was slightly down, obviously, as you might expect on 2019. But construction and building applications is together, construction and building applications make up about a quarter of our market. So in terms of collaboration on health and safety, surprisingly, we collaborate to try and achieve zero harm. I don't think that's a shock to anybody, is it? And we've got some really positive environmental performance. Like I say, we report on this every year. I'll let you get the SD report. This is the note that I want you to make, the mental note. David's already mentioned it. I'll come back to this later. But recent studies have shown lime captures that 33% of the process emissions that have to be produced to produce lime. So when you produce lime, you inevitably drive off carbon dioxide. Those are your process emissions. It doesn't matter how you heat it, you're going to get the carbon dioxide driven off. But in use, because we have such a diverse array of uses, 33% of that gets reabsorbed. So as soon as you put it in water for water treatment, 100% carbonisation of that particular product in that particular use. But overall, it's 33% based on the markets that the materials go into. Lime and stabilisation, suck your teeth. So basically, there are three mechanisms at work when we stabilise with lime. First of all is improvement. So if you add lime to a moisture-bearing soil, you get this exothermic reaction. So basically, lime and water heats up, essentially. According to my maths, that's for every kilo of calcium oxide you heat up, you get around about enough energy to boil 6 kettles. So that's quite a lot. That heat dries the soil, and it also reduces the moisture because the calcium oxide is combining with the hydrate, with the water to make the hydrate. So you're getting two actions going on there to help you dry out your soil. So basically I've done some more maths at the bottom. So if you add 3% tonne per tonne, 3% lime in tonne per tonne, so tonnes of lime to tonnes of soil, you generate enough heat to drive off around about 300 kilograms of water, and you chemically bind another 9. Key, and again, so this is the one thing I would say, and all the contractors in the room, I hope, would come and give me a pat on the back afterwards, because this is what I'm constantly told. Mixing is the key to any form of decent stabilisation or modification and improvement. Modification only happens with clay soils. So basically what happens is that you have wet and aligned clay particles, so they basically slip around. Very technical this is, isn't it? And then when you add your lime, you disrupt that water layer, you disrupt the position, and you get ion exchange of the calcium onto the surfaces, and that gives you less slip and therefore more strength gain in your soils. This is apparently quite rapid. It takes a couple of hours. So you've got a couple of mechanisms going on. You've got your drying out, then you've got your disruption, which is building up your strength as well. And then the last one is stabilisation. So this is the longer term reaction. This is where you are getting a chemical reaction with the silica and the alumina in the soils, and you get these silicate hydrates and aluminate hydrates being generated, and those are the sorts of similar to give you the pozzolanic reactions that you would get with the cement. So this is a much longer term reaction taking place over many years. Now again, this is the note that you need to make at the end. So basically there are two pathways. When you add when you add lime to your soil, you can either get calcium hydroxide formed, which is drives off your mortar and does your other bits and pieces, and then it goes down two routes. It either forms these sort of calcium aluminosilicate hydrates, which is your pozzolanic cementy reactions, or you get the calcium percarbonate route. Okay, so those are the two paths that it takes. So that's where I'm going to bring these two things together and talk about lime and the path to negative. So, couple of things going on here. Interestingly, this isn't something that, I know that the focus has been concrete and all of these sorts of things, but stabilisation is inherently a positive, resource-efficient, low-carbon construction methodology because you are using most often on-site materials. Okay, so you're reducing the demand to bring materials onto site, so therefore you're reducing transport, you're reducing fuel consumption as a result of that, you're reducing traffic congestion around the site, which it fewer delays means lower carbon. By stabilising the sites, you're also able to help sites be worked in wet weather. So what that means is that you've got less lost time, less stuff coming to site then going away again because it's not being used. So again, it's all that idea about it's just driving down your carbon all the time. And it therefore is delivering timely and cost-effective construction at the same time. So I'm not going to talk about this bit, okay, which is your kind of LCA bit of saying stabilisation is a really, really great thing to do for all of those reasons that we all know so well about being cost-effective, time-effective. Lime, I've got to say, David's already talked about this. Lime, basically, you put chalk and gas into a kiln, you heat it up, and you get lime out with processed CO2 and so on. And we've talked about the split 25-75. So the combustion CO2, we can do something about, we can avoid those. And again, David's talked about those, I won't focus on that. So the processed CO2 is unavoidable. Whatever we do, that's going to be generated. That's why we need the CCUS, okay? We're actively engaged in looking at that. If we think about saying, we're going to have CCUS, this is going to happen at some point in the future, because we need lime. And if we need lime, we need CCUS. And members are actively taking part. So David's talked about the peak cluster that he's involved in. Singleton Birch is based in the Humber. There's a massive cluster there. So we're looking about an industry that's probably going to be getting its carbon captured somewhere between 2030 and 2040. You know, we're looking at zero carbon generation at that point, at zero carbon manufacturing. There are three things that were going to lead us to this net zero approach then. Zero carbon fuels means zero emissions, okay? Carbon capture means zero emissions. So once we get those two bricks in place, carbonation, which is the atmospheric absorption of CO2 from the air, carbonation then makes us net negative, okay? So carbonation is a naturally occurring thing. If you leave lime outside, it will carbonate. That is the way of it. That's why we have to heat the limestone up to drive the carbon dioxide off, because it naturally wants to revert to calcium carbonate. And what that means is that it's also thermodynamically stable. So once you've recarbonated it, it's not like you're putting it in your fizzy pop, you take the lid off and the carbon dioxide goes back out again. That's it. Unless you're going to heat it up again to 1,000 degrees C, you've got calcium carbonate being formed. That's how air limes work. You know, that's what they do. That's the process. They are not hydraulic materials. They are not cement. They, you know, unless you're using them in a clay soil, air limes in mortars and things like that work by converting into calcium carbonate. So the work by EULA, European Lime Association, shows that in 8 conclusive uses, so in 8 uses where there is a lot of documentary evidence, you'd get at least 23% recarbonation. But there's another 10% which is likely to come from other uses as well, and that includes uses such as stabilisation. So what this says is that there is very, very solid evidence that we can hang our hat on that says it's absolutely, definitely 23%. And then there's evidence, but there's only maybe 10 papers rather than 50 papers that say you're probably going to get another 10%. And then there's a whole load of other stuff where there are no papers at all. So we're pretty confident that you're going to get 33%. So there was a case study in terms of stabilisation. There is this one key piece of evidence, which is a case study from Germany. It's one of these great projects where the stabilisation was done, and whoever was doing it at the time, it was new and it was innovative, and they took loads of measurements all over it. You know, so there's loads of data, loads of historical data. Unfortunately, somebody kept all of that. So they had this embankment constructed in 1979, and they added quicklime for improvement and stabilisation. I'm not going to go into the details, but essentially they went back and sampled it again in 1990, and they noted the increase in compressive strength. And the 1990 study was all about how much stronger it has got, how much has it reacted. They then went back again in 2013. So at that time, it's now 34 years old. Those compressive strengths had gone up to between 3.8 and 6 megapascals. So a significant strength increase over time, which you'd expect. But what was important about the 2013 study was that they noted that, remember the 2 pathways? Okay, 47% of the calcium oxide had gone through to the pozzolanic reactions, and the other 37% had been carbonated, calcium carbonate. And then you've got 16% that's still in there after 34 years of free lime. Okay, so what you are doing is one key study. They're looking for other studies at the moment where you've got a really good baseline of data and they can go back and start extracting some more information and trying to build a better picture about carbonation rates in stabilised soils. So basically, what that tells us is that if you are stabilising with lime in long-lived infrastructure, which is what mostly you're using lime stabilisation for, you're actually investing in long-term CO2 absorption because that's what's happening. It will be carbonating. That's just the way life is. When the sector achieves net negative, every time you use lime in a long-lived infrastructure asset, you are investing in in a contribution to achieving the UK achieving net zero by 2050. That's what it means, essentially. We need to achieve, no doubt that we need to achieve net zero manufacturing, and there's no doubt that we will achieve net zero manufacturing, but that means every time you use lime and you get recarbonation, you're actually capturing and extracting CO2 from the atmosphere, which has got to be a good thing.